The last time that we met, we were looking at molecular shapes, finishing up our discussion on VSEPR, and we came up with a series of structures, and this actually functioned as a couple of them, so let's play this game. If I only have two things attached, it's going to be a straight line. Okay. If I have three things attached, and we'll pull these off for just a second, then it's going to be this shape of a triangle or trigonal planar. Okay. When we got to 4, things got a little more complex because we had this tetrahedral shape, and things started falling apart. Now, here we go. We have this tetrahedral geometry, very symmetric, but it's three-dimensional. When we got to 5, then we had this sort of shape where we had linear crossed with the triangular planar. Again, we called that trigonal bipyramidal. It's two triangular pyramids. We did not build the octahedral the last time that we met. I want to do that very quickly this morning, because this is the last major shape that we need to concern ourselves with. That's where we left ourselves last time, was looking at octahedral. Say the right words. And again, if the nearly home. And as we talked about last time, that shape, that orientation is essentially just the Cartesian coordinate system. And again, we can think of it as just having a group at the top and bottom of the x-axis, the y-axis, and the z-axis. So again, trying to hold it, there we go. That may be a decent angle right there. Again, top and bottom, front and back, and side to side. So again, if we just think of the Cartesian coordinate system, I can draw some of these easily on the board. Some of them take a little more work. Again, 2 linear. And again, we're looking at the fundamental, the foundational, the electronic geometries. If all 3 groups are atoms, this is trigonal planar. With 4, again, we have to resort to these wedges and the dashes. And again, just remember, if it's wedged, it projects, it comes towards you. And if it's dashed, it recedes, it goes back. This is tetrahedral. And then 5 and 6. 5 is linear, crossed with triangular planar. Again, this is the one that has the ugliest name, trigonal bipyramidal. And the last one is octahedral. Go ahead and continue to use the wedges and the dashes there. That one sticks forward, that one goes back. So there you have them on the desk in front of you. Again, for those of you attending online. Okay, one more time. That's the 5 there. Okay, there's 2, there's 3. Together they make 5. There's the tetrahedral, that's 4. And then there is the octahedral, which again is for a steric number of 6. Now, theoretically then, we can draw a Lewis structure, or given the Lewis structure, we can then say, okay, great, how many things are attached to the central atom? Once we have that question, then we can say, okay, so what is the shape of that molecule going to be? And I will argue with you in general, okay, that we can at least argue a little bit on what the reactivity should be based upon the shape. If we were wanting to attack the central atom, if we were wanting to get something to bond to this central atom, the more things that are around it, the more difficult it is to get to that central atom. It's just like saying, if we've got a person and he's got a guard on his left and a guard on his right, we can come face forward or from the back and get to him pretty quickly. If there's 3, it gets a little harder. Pardon me, if there's 4, it gets a little harder. If there's 5, harder still. 6, one would say hardest of all. So there's going to be some argument that we can make based upon the complexity of the structure. Okay. We're going to pause here for just a second because I am dying in this sweater, because while it's cold outside, it is not cold in this room. So all right, made it without removing completely my hearing aids. All right. Why sheep don't freeze to death. Meanwhile, back at the ranch. Please back up really quickly. Perhaps one day we'll have a day that goes smoothly, but don't hold your breath. I'll still be involved. Okay, so what we want to do now is to look at these and argue. We've got the general shape. Now we want to argue the other thing that we want to discuss, and this is the critical thing. We're going to come at this from a number of different directions. Hopefully one of them will stick. But the bottom line here is I want you to be able to look at a Lewis structure and tell me whether it is balanced or not. We're going to use the word polar or non-polar. Polar means it's unbalanced. When we talk about something being polar, it's unbalanced. So we're looking at molecular polarity, or molecular polarity is an imbalance of electron charge, or imbalance of electrons. And again, as I write those 3 lines, it gets me again. I'm so glad I learned English as a child, because you would see the word imbalance and unbalance and think, why do we have both of those? Because English, right? It's like flammable and inflammable are both mean they burn, but inflammable means it doesn't. Yeah. Whew. All right. Now, we're going to base this on, so for a molecule to be polar, for a molecule to be polar, 1, it must contain polar bonds. So it has to contain polar bonds. And must not be totally symmetric. Must possess some sort of asymmetry. We come back here to polar bonds. Polar bond means we're going to have a difference in electronegativity. Here's the periodic table. Here's the noble gases over here. Don't worry about them. That's why I always separate them when I write the table, because we're not going to see 4 compounds of noble gases in this semester if we see that many. Okay. Electronegativity increases up and to the right, and fluorine is king. Fluorine is the king of electronegativity. On the Pauling scale, it has a value of 4. Nothing is bigger than 4. Okay? It's like he's got a perfect GPA. Everything is less electronegative than fluorine, is what I'm saying. Okay? So fluorine is at the top of the electronegativity scale. You may assume, well, forget assuming. The further apart things are on the table, the more polar that bond would be. Okay? An oxygen-fluorine bond is slightly polar. A nitrogen-fluorine bond is polar. A carbon-fluorine bond is quite polar, and a hydrogen-fluorine bond is so polar it's almost ionic. Okay. If we come down the table, a fluorine-chlorine bond is polar. A fluorine-bromine bond is more polar. A fluorine-iodine bond is more polar still. So the further away they get from each other, the more polar they will be. There are a couple of cases. A nitrogen-chlorine bond just happens to be almost nonpolar. It's very, very slightly polar. A carbon-sulfur bond is very slightly polar toward the sulfur. Okay? We talk about polarity increasing up and to the right. And generally speaking, that's the way we would apply it. If I ask you to make fine distinctions, I'll give you the polarity values. If it's something that I think is fairly obvious, then I won't. For instance, here's a difficult one, an oxygen-chlorine bond. Is it polar? Well, we would argue probably, because it's different. Which one is more polar, oxygen or chlorine? Do you have that information? Do you know that off the top of your head? Okay, it's actually oxygen. Okay, so it's one of those things where I don't expect you to know that. I do this for a living. I'm a chemist. Okay, so if I need you to do finer details, I'll just give you the electronegativity table. And as a matter of fact, I'm just making myself a mental note. I'm just going to put that at the end of our exam, along with a couple of other tables. It's not numbers that you need to memorize. If you're like me and you work with it every day, you know them. That is 3.5 and 3.0. Okay, and oxygen is more polar with the 3.5. Again, I know things, but that's what years and years are for. So, So let's look at this. Let's take this. Let's look at some of the example molecules that we've seen before. I'm going to come over here. I want to leave these structures on the board if I can. So let's consider carbon dioxide and say, okay, we're just asking the questions now. Is this molecule polar or nonpolar? Okay, so all we're doing now for the next few minutes is look at examples and assign polarity. Does it contain polar bonds? Yes, because a carbon-oxygen bond is polar. They're on the same row, oxygen's to the left, it's more electronegative. So does it contain polar bonds? Yes, it does. Does it possess some sort of asymmetry? I would argue no, it's perfectly symmetric. It's completely balanced. Yes, the oxygens are pulling out, but they're pulling exactly opposite directions. Okay. Am I looking at anyone here that loved physics and or calculus and vectors? Okay. So Hanson, if you'll just think in vector terms, I've got an electric dipole vector in this direction, an electric dipole in 180 degrees, and the sum of those two vectors would be 0. So there would be no vector sum. Okay. Now, for the rest of you, if I have two things attached to a common third, if they weigh exactly the same, so they're pulling electrons out, or tug of war, if they're pulling out both directions, what does the flag do? Doesn't go anywhere if they're pulling with equal strength. So that gives me a balanced. Just say this, is it symmetric? Are the two things attached to the central carbon exactly the same? Yes, it's not polar. Okay. The simple question is, when you say, what is attached to the central oxygen, and you go, two somethings, okay, then that's going to be symmetric. If we looked at this analog, okay, so by the way, so our argument here is that this is non-polar. Need to be writing that in blue or something so that we can see it. 1 and 3, missed it. Green it is. Okay, so that's non-polar. I would argue that OCS then must be polar because what's attached to the carbon? Oxygen and sulfur. If I swapped ends, we could see it. So it's not symmetric. It possesses asymmetry, and therefore it must be polar. I'll be honest with you. Okay, back up. My father was a pulpit minister most of his adult life. And he jokingly, but I watched him do it, so it wasn't really a joke for him, he would jokingly say, when someone tells me something and I go, okay, that's really going to be useful, I will say, so-and-so told me. And then the next time I use it, I'll say, I once heard. And then the third time, it's, as you know. And then the fourth time is, as I have always said, such and such. Someone told me, how do you do this the easy way? You say, if there is an and, then it's polar. And I said, he goes, it's very simple. Whoever this, I think it was it doesn't matter, this student. They said, when you ask the question, what's connected to the central atom? If you have to say such and such, it's probably polar. Okay, so if I say, what's attached to the central atom? 2 oxygens. It's not polar. What's attached? An oxygen and a sulfur. Okay, it's polar. So if you think that way, can you be wrong with that? Yeah, I can come up with an example that breaks the and rule. But if you're right 9 times out of 10, everybody's going to be happy. Okay? And after a while, you'll figure out the exceptions to the and rule yourself. Let's look at some steric number of 3. Here is borane, BH3. and we ask ourselves, does it contain polar bonds? Well, boron and hydrogen are separated by some distance on the table, so we would argue, yes, it's polar. Okay. You would have to know the numbers. Again, I do. Hydrogen is actually more electronegative than boron. It's higher in the table, so it's more electronegative. It's all right. But, so it has polar bonds. So again, so you've got dipole there, a dipole there, and a dipole there. You know what's happening on the force table. Life is good. What's attached to that central boron? 3 hydrogens. So is it polar or nonpolar? It's nonpolar, because I didn't have to use the and, or you would say it's completely symmetric. All 3 things attached are exactly the same. So this is non-polar. Contains polar bonds, but is totally symmetric. Again, I'm making an ugly board because I'm wanting to keep our basic structures up here. If we looked at something like formaldehyde, okay, the steric number on the carbon is 3. It's going to be trigonal planar. It has polar bonds. And I'm going to get a little explicit here. The carbon-hydrogen bonds, carbon is more electronegative. Okay, so here's the carbon, here's the 2 hydrogens. Those bonds are polar, so the carbon is relatively electron rich versus the hydrogens. It's pulling on those electrons. But the oxygen is pulling electrons up toward itself. And so if we just look at the arrows are all pointing up. And therefore it's got to be polar. What's attached to the central atom? 2 hydrogens and an oxygen. So it's not symmetric, it's got to be polar. Now I've added one thing here. Not only would we argue, is it polar? It has polar bonds and is asymmetric. Okay. Not only does it have polar bonds, I don't want the green one, I want the blue one. It's polar, and we would argue that it's negative up here and it's positive down here. That's a lowercase Greek delta. It just means part or partial or change in this context. So we would argue that this end of the molecule is more negative and this end of the molecule is more positive. Okay? I don't want to beat you up with this, but this is an example that I think carries everything I need you to be able to do when you look at a structure and tell me everything I need you to be able to tell me about it. So let's look at this. I want to ask all of these questions and hopefully get to a point where we can all answer it. We say, okay, great. Is this a valid Lewis structure? I'm going to erase these dipole arrows here because it's a little bit ugly, okay? Okay. Carbon is making 4 bonds, has no lone pairs. Oxygen is making 2 bonds, has 2 lone pairs. That's great. Hydrogen is making 1 bond. If we go through and count the electrons, that's the proper Lewis structure for formaldehyde. We've seen that. We also note that there is a carbon-oxygen double bond. That means between those 2 atoms there are 4 electrons being shared because it's 2 bonds. So we've got a bond here that is susceptible to attack because there's a lot of electrons there. Okay? I'm going to continue to pick on Hansen a little bit this morning because he's got on his bank robber mask this morning, and they asked they asked Billy the Kid why he robbed banks, and his response was, "That's where the money is." Which, again, pretty good sense. Now, if something comes along with a positive charge, let's suppose we had H plus, a proton. We have H plus come along. Where's it most likely to attack? Somewhere up here around the oxygen, because there's a double bond, there's two lone pairs. Everything that a positive charge should want is right here. If H plus bonds to the oxygen, one of those bonds has got to break, because oxygen can't have 10 electrons around it. So if it makes a bond with something else, then it's got to break a bond with something else. So not only could it react in terms of polarity, should it react, but now we've got some idea of how it might react. On the other hand, if we had this molecule, one more time, and I attack this with Cl minus, okay? Again, we labeled this end of the molecule, just going to put I can't miss it. We labeled this end of the molecule as being more negative and this end of the molecule as being more positive. So if I've got a negative charge, it should attack this negative charge should attack the carbon. Negative should be attracted to positive. If chlorine is going to make a bond to that carbon, can carbon make 5 bonds? Shake your head side to side. No, cannot. That means it's going to have to give up a bond. And we would get something that looks, or we can get something that looks like this. When you finish your first semester of organic, you're going to be doing this stuff and not even thinking about it. You're going to go, yeah, that's clearly what that would do. What I want you to be able to do in this greater, broader context in this course is, if I were to give you this, I would go, talk me through this. And you would say, okay, great, this carbon-oxygen bond is polar, and the carbon is electropositive, so the negative charge is attracted there. Carbon can't make 5 bonds, so it has to give one up, and this is what, and that could be a possible product, okay? And that's going to be one of those questions where I'm going to grade that purely on your attempt to explain it, okay? And any attempt is worth something, and if you give me everything I want, it's 4, and if you give me almost what I want, it's 3, 3.5, okay? But we need to be able to ask and answer, is it polar or not? And then eventually, because that's why we care whether it's polar or not, how then might it react? And again, once we can figure out that it's polar and we can figure out which end is negative and which end is positive. The negative end, positive things attack. The positive end, negative things attack. And we just know that if it was making the right number of bonds, to make one, it's got to break one. Or to break one, it's got to make one, perhaps. Okay. So, there is that. Now, again, that was really one step beyond where I had intended to go today, but it was there, and I thought we're just going there. Let's quickly look at a steric number of 4. And here is our model for methane. I'm going to hold this up, then I'm going to go write it on the board. Okay, here is methane. And let's just jump straight to the chase. Polar or nonpolar? Why do you say that?
Because
That's fine. Look at that molecule right in front of you there, because there it is.
symmetric.
Okay, it's symmetric, and therefore it must be nonpolar. Okay, I thought you were thinking correctly. I thought you just said the wrong word. All right, excellent. This is symmetric, and therefore non-polar. Just remember that symmetry and polarity are opposites. Polar means unbalanced, symmetric means balanced. What's attached to the central carbon? 4 hydrogens. Did use the and word. If we look at, by the way, that was methane. If we have this molecule, which is oddly enough chloromethane, it's methane with a chlorine attached. Now, polar or nonpolar?
Polar.
It's polar now, because this bond, chlorine is pulling electron density toward it. Each of the CH bonds are slightly polar toward the carbon. So once again, Hansen, if we look at vector sum, everything's pointing up. The net vector sum is up. Okay. Or what's attached to the central carbon? 3 hydrogens and a chlorine. Okay. And because we've said 3 of something and 1 of another, it's probably polar. That's going to be the case. It's not totally symmetric. It's now asymmetric. If we look at and again, I'm doing a little nomenclature here as well. In general, unless I specifically tell you, that's just for you to see now and learn from Dr. Boston with these organic stuff. This is dichloromethane, which actually makes some sense. The organic guys sometimes are pretty good to keep us on task. Dichloromethane. Now, is it polar or nonpolar? It's nonpolar?
No, it is polar.
It is polar.
Because it's half and half.
It is polar because it's connected to 2 chlorines. You're kidding. And that rolled under the table, of course, by the mechanics rule. I need it back. And that ball was actually too big to fit under there, and yet it still did. Don't ask me how. Okay. If we look at this, and here is, by the time we get here, I think it's always in our interest to build and to examine the model when we get this far into this. Say, okay, great. Here are the chlorines at the top, or as I've drawn it. Here's the molecule as I drew it. Chlorine to the left, chlorine up, hydrogen in the front, hydrogen in the back. Okay? If it wants to balance, okay, notice that the chlorines go to the bottom because they're bigger. Okay, gravity takes it that way. If we think electronically, the electrons are being pulled that direction. So down here is negative, up here is positive, and that means it's polar because it's got a pole, positive pole, a negative pole. If I try and get it to balance here, won't do it. Even if I try to get it balanced here, gravity still pulls the. We knew that would happen. Gravity's going to pull those suckers down. So again, is it totally symmetric? No, and therefore it must be polar. If we go one more case, So this is blue pen. This is still polar. If all four are the same, it's nonpolar. If one is different, it's polar. If two are different than the other two, it's polar. If we have this, and I'm going to purposefully write it this direction. Here is trichloromethane. And again, 3 chlorines. So trichloromethane. Taylor, you're on a roll. Polar or nonpolar?
Not polar.
It's polar because one of these things is not like the other. One of these things just doesn't belong. My kids grew up in the Sesame Street era. I grew up in the Captain Kangaroo era. And if I say Captain Kangaroo, has anyone in here ever seen any of the Captain Kangaroo show? But now you're thinking, I may have to go look that up. Here is the theme song. Yum dum 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 dum. Very catchy. If you're a young child, you sit in front of it and go, what's he going to do next? Bunny Rabbit was on that show. Hey, 3 chlorines and a hydrogen. Okay, it's polar because I use the and word, 3 and. And then finally, if we get to dry cleaning fluid, also known as carbon tetrachloride, tetrachloromethane, nonpolar. She finishes strong as she started, nonpolar. Because what's attached to it? 4 chlorines. So it's symmetric. I'm going to now step back over here. I'm going to sketch a couple of 5 or 6s, and we're just going to, without doing much else, but just looking at it, go, okay, polar or nonpolar. So here we go. Let's test. This almost looks like a test question. Consider the following Lewis structure. Would this molecule be polar or nonpolar? Nonpolar, because it's connected to 5 fluorines. Okay. It's got a steric number of 5. That means it's going to have this shape. Okay. But the bottom line is all 5 things are the same. So the net pull, we know fluorine's pulling out, but it's pulling out in all the same directions. Okay, so it is nonpolar. It is totally symmetric. Polar or nonpolar? Polar, because? And. Okay. Because it's bonded to 3 fluorines and 2 hydrogens. If we were to consider electronegativities, fluorine is this way, hydrogens are this way, everything, so the net, pardon me, got that one out, the net pull is toward the fluorines. Again, it would be unbalanced toward the fluorines.
Does symmetry refer to size?
Pardon?
Does symmetry also refer to size?
No.
The size of it, because the electronegativity, like the atoms to the top right are bigger, right? So it would be heavier.
Symmetry really refers to how things are arranged around the central atom. Okay, we don't really care what. For instance, let me give you this example and see if it answers your question. I hope it will. Symmetric or not? Symmetric. So this is nonpolar. Okay, this is nonpolar, it's symmetric. Polar or nonpolar? Nonpolar because it's still symmetric. Does that answer? Does that speak to your question? Or were you asking something I missed?
The space filling model.
Ah, okay.
Because it doesn't really matter what shape it is. It's just like how much space it takes up. Do you think that's why?
Fluorine is always going to take up more space than hydrogen. Fluorine is the most electronegative because it has the greatest nuclear pull relative to its size. Okay? So that's what gives it the highest electronegativity, at least according to Pauling's theory. Okay? Okay, we've got 1 minute left. We've got now the tools in front of us that, given a Lewis structure, we can describe its steric number, we can describe its electronic geometry, where all of the electrons are. If it's got lone pairs, we can assign a molecular geometry. And by the way, I should have done that. I'll do one real quickly. And then, given its geometry, can we determine its polarity? And I think we found that to be true quickly. And I can't believe I let you get this far without this example. Here we go. I'm going to make this. I'm going to draw this like this to try and fool you. Polar or nonpolar? Polar. Why?
I just know because it's water.
Because it's water. Okay, it's polar. What's the steric number? 4. 2 atoms, 2 lone pair. So let me ask this question. What's attached to the central atom?
2 hydrogens and 2 lone pairs.
2 hydrogen and 2 lone pair. If we draw, see, and this is where we're not trying to be tricky, but I just drew it that way because it's the easy way. The better way to draw it would be to do this. If I drew it like that, then you would say to me, oh, that's polar because it's bent. That means it's not symmetric. Bent is asymmetric. Contains polar bonds. It's not perfectly symmetric. It's polar. It didn't intend to be a trick question. That's just the one that if we don't see it first, the next time we see it, we'd go, wait, you didn't show us that one. And now I have. All right. Great. Thank you for your attention. I'll see some of you this afternoon in lab, and I'll see the rest of you on Friday.